Yes, ma'am.
Okay. So, good morning to all. So, good morning, everyone. Today we start sampling. So, first I give brief introduction. What sampling? Some There is some conditions when a continuous time signal can be completely represented by and recoverable from knowledge of its value or sample at point equally spaced in time. The importance of sampling lies in its role as a bridge between continuous time signal and discrete time signal. As we will see in this chapter, the fact that under certain conditions, a continuous time signal can be completely recovered from a sequence of its sample provides a mechanism for representing a continuous time signal by a discrete time signal. So, what does mean by this is sampling actually that means recovering of the signal. When a continuous time signal is converted into digital discrete time signal and discrete time is converted into continuous time signal. So there is some losses of frequency. So when you recover the signal from one form to another form, that is called sampling. Suppose a given signal is discrete time signal and you have to find the continuous time signal. So based on the some sample, not all the sample, based on some sample, you can easily recover the original signal, that is continuous time. So this is called sampling. Sampling is also frequently performed on discrete time signal to change the effective data rate, an operation termed subsampling. So in this case, the sampling process discard certain value of the signal. Sampling is the process of converting a continuous time signal xt into a discrete time signal xn by measuring the amplitude of the continuous time signal xt at integer multiple of a sampling interval ts. So this is shown in figure 8.1. The figure A is a continuous time signal where x axis time and y axis is amplitude. So when you convert into discrete time signal, so for converting into discrete time signal, there is some sampled version. Suppose there is Ts is the one discrete value where the amplitude is x of Ts. Similarly, for 2Ts, the amplitude is 2 twice Ts, x of twice Ts. So for different value, there is some discrete value. For continuous, there are continuous so many values, but for discrete value at a particular interval, that is Ts, twice Ts, thrice Ts, only for this discrete value there is some amplitude, and based on this amplitude, that is xts twice x of 2Ts, x of 3Ts, based on this value you can convert the discrete time signal into continuous time signal. So this is sample version of this continuous time signal. Now what is sampling theorem? So sampling theorem for low pass signal. This theorem states that a band limited signal. What is band limited? That is signal where is the frequency is a range of frequency. Suppose the frequency is from W to 3W. Okay, so this is particular what is band limited. 3W minus W, that is twice W. So twice W is the range of the frequency, that is band limited signal. A finite energy which has no frequency component higher than WH radian per second or FH hertz may be completely recovered from a knowledge of its sample if the sampling frequency, that is omega s, is greater than or is equal to twice of WH sample per radian per second, or you can say that sampling frequency, that is Fs, is greater than twice of Fh sample per second. So for low pass signal, sampling theorem states that you can completely recovered from a knowledge of its sample if the sampling frequency Ws is greater than twice of Fs. So this is the main theorem कि यदि आपकी sampling frequency twice WHS से greater होगी और equal होगी, then only you can completely recover the original signal. Okay, original signal, that is continuous time signal. So this is the main condition. Sampling frequency is greater than or equals to twice of WH. So the minimum sampling rate or minimum sampling frequency is equal to twice WH is referred to as the Nyquist rate. So this is Nyquist rate. What is Nyquist rate? This is in the form of यदि band limited कहते हैं, so this is W2H and only frequency कहेंगे, तो this is twice FH and its reciprocal, that is twice W upon WS, or you can say that 1 upon Fs, or you can say that 1 upon twice Fs measured in second is called Nyquist interval. So there is a difference between Nyquist rate and Nyquist interval. Nyquist rate is, that is time interval Ts, and Nyquist interval is the frequency. Okay. So we can also express the sampling theorem in terms of maximum sample spacing rather than a minimum sampling rate, because the time interval, that is Ts, is equal to 1 by Fs, or you can say that it is less than 1 upon twice Fs. Hence the maximum sampling spacing for complete specification of the continuous time signal is 1 by twice Fs, and sampling a signal at a rate that is less than or greater than the Nyquist rate is referred to as the undersampling or oversampling. So जो आपकी main sampling है, this is also two types, undersampling and oversampling. So if the sampling interval or sampling rate is less than the twice Fs, so in this case the sampling is called undersampling, and when it is greater than, so it is called oversampling. Okay, so the xt is the continuous time signal, okay, original signal, and its discrete time signal is shown in figure B, and its range band limited signal है, so its range is minus WS to WH. Okay, so when you sample with ST, and ST is a signal with impulse response is 1. Okay, and range is minus T to plus T. So its frequency response becomes SW, which is also vary from minus WS2, this is minus W2 plus W. And for each discrete value, that is first discrete value is WS, second discrete value is twice WS. Similarly, in negative side, this is minus WS and twice WS and so on. So this is sampled signal when the continuous time signal, this is xt, multiply by the discrete B is spectrum of xt. आपने इसे जो हमने sample signal लिया है, this is a impulse signal. When this signal is multiplied, so this is figure E. This is called sampled signal. So for each value, that is Ts, there is amplitude xts. For time interval twice Ts, amplitude is x of 2s and so on. And this is x del W, this is spectrum of the sample signal. So the figure, that is A, C and E in continuous domain, and this is in time domain, and figure B, D and F in frequency domain. Clear? So let xt be a continuous time signal. Let this signal be of finite energy and band limited. That is, xt does not contain any frequency component higher than the WH radian per second. A sampling signal samples this signal regularly at the rate of WH sample per radian per second. Okay, this is for figure B. The time spacing between any two successive sample is Ts. So figure 8.T shows the sampling signal of frequency equal to sampling frequency Ws, and the figure E shows an instantaneous sample version of xt. Suppose यदि आपको कहा कि at the discrete value twice Ts, इस पे sample signal की value क्या होगी, तो you can easily observe that this is x of twice Ts. So as per figure C, the figure C is an impulse train. So this impulse train can be represented or expressed in this form mathematically as T is summation n minus infinity to plus infinity del T minus n Ts. Okay, so del T is 1, and for there, because there are different values of Ts, that is Ts, twice Ts, thrice Ts, and last sample is NTS. So this becomes T del T minus NTS. The sample signal x del T in figure E is obtained by multiplying the signal xt with the impulse train xt. Okay, so mathematically you can express this xt multiplied by del T. Okay, then because of sampling property of unit impulse, we know that multiplying xt by a unit impulse sample, the value of the signal at the point at which the impulse is located, that is xt multiplied by del t minus t naught. So this becomes x t naught del t minus t naught. So as per the impulse property, what is the impulse property? When any input, any signal is multiplied by a impulse signal. So suppose impulse is located at t naught point. So the impulse signal becomes del t minus t naught. So when xt is multiplied by del t minus t naught, so that the original signal is, that is xt becomes 1 at interval t naught. So this becomes, in place of t, you can put x t naught del t minus t naught. So applying this equation, we can see that x del t is an impulse train with amplitude of the impulse equal to the sample of xt at interval space by ts. So mathematically this x del t represented by summation and varies minus infinity to infinity. This xt, so xt replaced by nts because there are nts discrete value. So x nts multiply by del t minus nts. Since the width of the impulse in x del t approaches 0, it represents only instantaneous value. Therefore, this method is called instantaneous sampling. Taking the Fourier transform of equation 8.3 and using the multiplication property of the Fourier transform. So, this equation 8.3 is x del t into st. Okay. So, as per the multiplication property of Fourier transform, the Fourier transform of a when two signal is multiply, which is equals to 1 upon 2 pi into convolution of these two signals. So xt का convolution, sorry, xt का Fourier transform xw and del t का Fourier transform sw. So convolution of these two signal multiply by 1 upon 2 pi. We know that Fourier transform of a periodic impulse train in time domain with period Ts is periodic impulse train in frequency domain with period Ws is 2 pi by Ts. Okay, so this Sw becomes, this is equation 8.2d. What is 8.2d? This is 8.2 and varies from minus infinity to infinity del t minus nts. So this x del t is x of nts del t minus nts. Since the width of the impulse in xt approaches 0, it represents only instantaneous value. Therefore, this method is called, okay, this already done. This expression, we know that the Fourier transform a periodic impulse train in time domain with period Ts is a periodic impulse train in frequency domain with period Ws is 2 pi by Ts. So you can multiply 2 pi by Ts. Okay. आपका जो st था, st is del t minus nts. So इसका frequency domain क्या हो जाएगा? 2 pi by Ts del w minus nws. Okay. Now substituting this value as w in this expression, this is x del w 1 upon 2 pi. So put here, so this becomes 1 upon 2 pi. Okay. And xw, then convolution, then del w. So del w की value put from 8.7, and when you solve this, so this becomes 2 pi cancel and 1 by ts take outside, xw convolution, this summation and varies from minus infinity to infinity del w minus and ws. So since convolution with an impulse simply shift a signal as per the shifting property of Fourier transform. Okay, so this becomes, because xw convolution with a impulse, and this impulse is for nws value, this is 1. So you can replace xw by xw minus ws because impulse is at w minus w nws, or you can say that w is equal to nws. nws पे आपका impulse 1 है, so when an impulse is multiplied by a input signal xt, and xt का जो Fourier transform है, that is xw, so this is also shifted by w minus ws. Clear? Then x del w is equal to 1 by ts and varies from minus infinity to infinity x, w minus and ws or equivalent. In f domain, frequency domain में you can replace w by f. So this become 1 by ts x f minus and fs. Or when you can expand this expression, okay, for different value. So this becomes, for negative value, this is w minus w minus the 2ws. So this become w plus 2ws. This is w minus ws. So this become w plus ws. Similarly, this x w minus x 0. So this is x w, then x w minus ws, then x w minus twice ws, and so on. From both sides, minus infinity to plus infinity. So this equation, that is 8.8, represent the spectrum of the sample signal x del t. Thus, the Fourier transform of the sample signal is given by an infinite sum of shifted version of the original signal. That is Fourier transform xw scaled by 1 by ts. So there are three cases. First is when sampling frequency is greater than twice the original frequency, that is WH. So in this case, there is no overlap between the shifted replica of WH. So xt can be recovered easily exactly from x del t by means of a practical low pass filter with gain Ts and a cutoff frequency, that is Wc, greater than Wh and less than Ws minus Wh. So the cutoff frequency ranges between Ws to Ws minus Wh. Okay, you can see this figure. This is figure number 8.3a. Okay, the input is given, okay, with a multiplier, and input is multiplied with a impulse xt, is multiplied with a impulse xt st. So this become x del t is the output, and their Fourier transform, that is x del w. When this signal is feed into a low pass filter, and low pass filter is a ht, and its frequency transform is hw. So you can recover the original signal xt, and which is equal to xw in the Fourier frequency domain. So xw is x del w multiplied by hw. This x del w multiplied by this hw. Second figure, that is B. This is आपने जो जिसे सैंपल कर रहे हैं, that is WH है ना. So this is the plot of WH and frequency transform, that is XW versus W. Now when XT is multiplied by del T, so this becomes a discrete value, and range of frequencies minus WH to WH, because here sampling frequency is greater than WH, so there is no overlapping. You can easily observe one value WH and there is some space, then the next sample is start. Is it visible? Hello? Okay. So in figure C, this is x del W. What is x del W? This is, okay. आपने यहाँ input xt दिया, then sampled version है xt, so xt multiply by, so output is x del t, so this is x del t. Clear? इसका frequency domain के form में है, and this is xw, this is input. So, and what is HT or HW? HW is its cutoff frequency is minus WC to plus WC. So there, this is twice WC. This is the frequency of low pass filter. So this is the output. XW is equal to X del W into HW. So only one signal, one discrete, one sample is formed. Remaining sample is filter. So exact recovery of a continuous time signal from its sample by using the ideal low pass filter. So from this sampled version, you can find the original signal xt. This is xt. Okay. And xt का जो frequency domain में है xw, and this figure B and figure E both are equivalent. That means the original signal is completely recovered. Second case, when sampling Ws is equal to twice Wh. In this case, when Ws is equal to twice Wh, there is no overlap between the shifted replica of Xw. So Xt can be recovered exactly from X del T by means of an ideal low pass filter with gain Ts and a cutoff frequency Wc is equal to Ws. So this is X del W. There is no overlap as shown in the previous figure. In the case of case 1 में वहां पे WH and next WH, that is WH and twice WH के बीच में there is gap, and there is no gaps, that means there is no overlapping. And this is HW. So XW is X del W into HW. Third case is there is some difficulty to recover the signal because the sampling frequency is less than twice the WH. So in this case, aliasing is possible. When WS is less than twice WH, that is undersampling, there is an overlap between the shifted replica of XW. Consequently, XT cannot be recovered exactly from X del T, even by means of an ideal low pass filter. Overlap in the shifted replica of original term spectrum is termed as aliasing. So what is aliasing? When there is overlap between the shifted replica. Okay, when there is overlap between WS and WS. So this is termed as aliasing. Overlap in the shifted replica of original spectrum is termed as aliasing, which refer to phenomena of a high frequency component in the spectrum of the signal, seemingly taking on the identity of a lower frequency in the spectrum of its sampled version. So overlap between the replica of XW centered at W is equal to 0 and at W is equal to WS. This occurs for frequency between WS minus WH and WH. And these replica add, and thus the basic shape of the spectrum change from portion of a triangle to a constant. And you can easily see in figure 8.5. This is the frequency, figure 8.5. This is called aliasing because this is original signal. One form of frequency, एक आपका frequency यहाँ WS है, दूसरा WH है. Okay, so this is FS, that is WS, and जहां आपका WH लिख रहा है and this is WS. तो यहाँ से start होके एक आपकी जो frequency यहाँ से start हो रही है and दूसरी frequency यहाँ से start हो रही है. So there is overlap between two replica. So this shaded portion is WS जो शेडेड पोर्शन है उसका एक पॉइंट दिस इज WS माइनस WH है एंड दूसरा पॉइंट इज WH. So from this spectra you can see that the spectra cross at frequency WS by 2 and this frequency is called folding frequency. जहां पे आपका स्पेक्ट्रा क्रॉस हो रहा है the frequency is WS by 2 मतलब आपकी जो सैम्पलिंग फ्रीक्वेंसी है उसकी हाफ फ्रीक्वेंसी पे ये स्पेक्ट्रा क्रॉस हो रहा है. So this is called folding frequency also. And the spectrum, the component of the frequency above the WS by 2 मतलब सैम्पलिंग फ्रीक्वेंसी से हाफ से जो ग्रेटर साइड पोर्शन होगा reappear as component of frequency below WS by 2 and this tail version is known as the spectrum folding or aliasing. So to combat the effect of aliasing in practice, we may use two corrective measures. First measure is जब भी आपको कोई किसी सिग्नल को सैंपल करना है, so before going to sampling, a low pass pre-aliased filter is used to attenuate those high frequency component of the signal that are not essential to the signal, that are not essential to the information conveyed by the signal. So suppose आपका suppose यदि आपका सिग्नल है उसमें हाई फ्रीक्वेंसी कंपोनेंट है जिसकी इंफॉर्मेशन का आउटपुट हमें वो यूज नहीं है सो दैट यू कैन अप्लाई अ लो पास प्री अलाइज फिल्टर सो दैट द हायर फ्रीक्वेंसी आर filtered. And second point, the filtered signal is sampled at a rate slightly higher than the Nyquist rate. और जो filter signal होगा उसको आप sample करेंगे using the frequency slightly greater than the Nyquist rate. So the use of sampling rate higher than the Nyquist rate also has the beneficial effect of the easing the design of the reconstruction filter and used to recover original signal from its sampled version. So some example. In this example, you have to find the Nyquist rate or Nyquist frequency like this. So suppose a given signal xt is sine of 200 pi t. So you can compare with xt sine w1 t. So here w1 is 200. Okay. Okay, so W1 is 200 pi. So what is F1? F1 is half the W1. So this becomes 100. Therefore, the Nyquist rate is, what is Nyquist rate? That is WS, sampling frequency, and sampling frequency is twice the W1. So this becomes 400 pi, or in terms of Fs, Fs is twice of F1. So this is 200 Hertz. In second example, xt sine square 200 pi t. So this equation can be compared. First of all, you convert into, using the trigonometry identity, you convert in this form. So this becomes a naught minus a1 cos of omega 1 t. Here omega 1 is 400. So f1 is half the omega 1. So similarly, you can find the sampling frequency. Sampling frequency is twice the original frequency. So this is 800. And similarly, Fs is twice of F1. So this is 400 Hertz. Sorry. So second example, please hold for 2 minutes. Okay. Example 8.2, specify the Nyquist rate and Nyquist interval. So given signal xt is, this is a sinc function 200t. So first of all, you write the sinc function. How can you write sinc 200t? This is equal to sine 200 pi t. This is sinc function. So this is w1t upon w1t, and w1 is, this is 200, and f1 is half the w1, so this is 100. So what is Nyquist rate? Nyquist rate is twice the w1, so this is 400 pi, and this is frequency, so this is twice f1, this is 200 hertz. Very simple. Similarly for second, this is sinc function whole square 200 pi, so you can write sinc sine whole square upon 200 pi upon 200 pi ka whole square. So when you solve t, so you find omega 1. Okay, so you have to mark your attendance. Okay. Okay, so this example 8.3, a continuous time signal xt is obtained at the output of an low pass ideal low pass filter with cutoff frequency 1000 pi. If instantaneous sampling is performed on xt, which of the following sample period would guarantee that xt can be recovered from its sample version using an appropriate low pass filter? So there are three frequency, that is TS is 0.5 multiplied by 10 to the power minus 3. Another one is 2 into 10 to the power minus 3, and third one is 10 to the power minus 4. So how can you solve? First of all, see xt is obtained at the output of an ideal low pass filter with cutoff frequency is 1000 pi. That means the maximum frequency present in the signal is, this is, you can denote by W maximum, which is equals to 1000 pi, or F maximum is half the W maximum, so this is 500. Therefore, the sampling frequency is greater than or equals to twice W maximum, or you can say that greater than or equals to twice Fm maximum. So Nyquist rate, that is Nyquist rate is time interval, so Ts is less than or equal to 1 upon twice F maximum. So this is equals to 10 to the power minus 3. So from these three options, only A and C satisfy this condition. A and C. A is 0.5 into 10 to the power minus 3, and C is 10 to the power minus 4. So only these two conditions satisfy the Nyquist rate. Another example, xt be a signal with Nyquist rate is W naught. Determine the Nyquist rate for each of the following signal. सभी के लिए आपको नाइक्वस रेट फाइंड आउट करना है, दैट इज W नॉट. ओके, फॉर different signal. First signal is xt plus 1. If signal xt has a Nyquist rate is twice W maximum, then the maximum frequency present in the signal is half the W naught by 2, which is equal to W maximum, and its Fourier transform xw is 0. xw 0 क्यों होगा? Because xt plus 1. Okay. For mod value of W is greater than W naught by 2, and note that when the frequency of the signal changes, the Nyquist range change accordingly. So, if given xt, its Fourier transform is xw. So, what is yt? yt का ट्रांसफॉर्म yw. So, xt plus 1 को हम कैसे लिख सकते हैं? ट्रांसफॉर्म के फॉर्म में, because this is a shifting property. Okay, so this becomes xw e to the power j omega. So clearly yw is 0 for w is mod value of w is greater than or equals to w naught by 2, and the maximum frequency present in the signal, that is yt is equal to xt plus 1 is w naught by 2, and time shifting operation does not change the frequency of the signal. Therefore, Nyquist rate for xt plus 1 is same, that is ws is equal to w naught. Similarly, solve another examples. So in this sampling, you can solve maximum Nyquist rate and Nyquist interval. This is if the Nyquist rate, example 8.5, if the Nyquist rate of xt is ws, find the Nyquist rate for each of the following signal. First is x2t, second one is xt by 3, and third one is xt convolution with the xt, that is just like a autocorrelation. Okay, so first you can transform xt into frequency domain. So this is xw, and yt is given, this is x of 2t. So yw becomes, because this is here a scaling property, as per scaling property of Fourier transform, this becomes 1 by 2 x w by 2, and when yw is 0, for which value the frequency w is greater than w naught, and maximum frequency present in the signal is w naught, and the time scaling operation change the frequency of the signal. Therefore, Nyquist rate of x2t becomes 2 times w. This is not much important. Now, in next class, we can discuss the sampling technique, different type of sampling. Okay, like ideal or instantaneous sampling, which already discussed, natural or chopper sampling, and flat top sampling. I will also upload some notes, because this is only the books and not all the portion is necessary in your syllabus. Okay, so because a book is very vast, so I upload in classroom the some notes of sampling, okay, which is very specific for your BTech level course. So any doubt? So in next class, we can start the type of sampling. So today you only study what is sampling and how can you sample a signal, how can you recover the signal from the original signal, and what is the Nyquist rate, Nyquist interval, all these things, and how can you find the Nyquist rate and Nyquist interval from a given equations. Any questions? Sakshi, roll number 17, Sakshi. Are you present, Sakshi? Sakshi, roll number 17. Am I audible, Sakshi? He is writing in chat. Okay. Okay. PC user. Okay, mic is not working. Okay. Akash Jha. Akash Jha, roll number 44. I think people are only join the class and not listening. Animesh.
Yes, ma'am.
Okay, then Deepak Sharma. तो मैं अब नेक्स्ट क्लास जो भी लूंगी उसमें अटेंडेंस ऑनलाइन नहीं लेके अब मैं ऑफलाइन लूंगी अटेंडेंस। आपके नाम जिसके भी यहाँ पे ऑनलाइन विजिबल हैं सबके नाम लूंगी, देन आई मार्क द अटेंडेंस।
यस मैम।
है ना, क्योंकि बच्चे लोग बिल्कुल रिस्पॉन्ड नहीं कर रहे। 2-3 बच्चों को थोड़ा ना पढ़ा रही हूँ मैं। यू आर इन दी स्ट्रेंथ ऑफ 65 स्टूडेंट एंड ओनली 35 or 40 स्टूडेंट प्रेजेंट। फिर एग्जाम्स आएंगे, फिर आप कहेंगे कि मैम असाइनमेंट ले लीजिए, ये कर लीजिए, वो कर लीजिए, बस हमें मार्क्स दे दीजिए, तो वो पॉसिबल नहीं है बाद में फिर। Okay, then you may leave now. Here I end the meeting.